The purpose of this lab was to compare the model in theory versus the tested model and to observe whether the tested model holds up against the theory model. The observed model will be a video, and the theory model will be the VPython model without the drag component, as I will explain later. The assignment in this lab was to drop an object and record a film of the object being dropped. For my lab, I chose a foam ball as it was lighter than a baseball or a lot of other balls. This ball did the best at falling at a slow rate due to drag. The purpose in this was that the ball was fairly aerodynamic but still amassed enough drag for an ideal observation. I recorded a film of the ball falling and uploaded the film to tracker software provided. First, I cut the video to the appropriate length and calibrated tracker to the size of the ball. The ball was 6.5 centimeters in diameter and weighed about 55 grams. I then plotted each point of the ball falling at chronological frames that served as the points for the resulting graph. Here's a short clip of the video. Now let's take a look at the forces that act on the ball in the video. For this experiment, the ball is the system and the surroundings, such as the air, is everything else. The ball is experiencing the force due to gravity downward, that is the acceleration due to gravity times the mass of the ball. But it is also experiencing an upward force due to the force of drag, that is the drag component b times the square of the average velocity of the ball. Both equations are written here and will be used in coding later in the video. Arrows indicate the direction of the forces acting on the ball. The force of gravity is larger than the drag force as the ball does not remain in midair and does not travel upward. With the plotted points from Tracker, I was able to gather data both in a table and a graph, as you can see on the left. For this experiment, I only needed the data from the time and the y coordinates, as the ball only travels in the negative y direction. The data will be later important. Then I opened the code provided for this lab in the VPython software and changed the calculation loop by changing the net force to gather the new velocity as the ball is falling. And I changed the time frame to the first 0.534 seconds so that the data matches up with later with the tracker data. I also changed the change in time delta t to a much higher number, 0.01. The reasoning for this is that it decreases the spacing between the plotting points and does not actually interfere with the data. I set up two different codes, one with the drag component b and one without it. I gained b through trial and error until the data matched. This will matter later as we get two different results. The data from VPython includes the time required for each and the position of the ball. I then ran both codes as you can see here. The two graphs produced by VPython are very similar and we cannot tell a difference yet. However, we can see the yellow position vector. I then recorded the data in Excel, and I also recorded the data I got from Tracker in Excel. Afterwards, I created 4 different graphs, one for each set of data and one for all 3 sets of data where the scatter plots overlap. The first 3 serve as a reference, as it is sometimes hard to read every data point on a graph where points overlap in part. As you can see in the last graph, the data from all 3 are very close. If we zoom in, we can see that the graphs are still very close. However, the VPython graph, without the drag component b, has a lower value for the last position. But why are the graphs so close? The reason for that is that the spacing of the VPython data are very close. If delta t had remained 0.002, the frames for each position would have greatly increased, and the graphs would yield a much more noticeable gap. But we can see that the table data will still yield the accurate results. The final position of the ball in Tracker is the same as the final position of the ball in the simulated VPython model with the drag component. As a result, the recorded model does not hold up against the theory model that doesn't include a drag component in the formula. The model with the drag component was a model we had to edit to simulate real-world scenarios that include air, but in theory everything occurs in a vacuum, and therefore the final position of the ball without drag is lower because drag is not acting upward to slow the ball down. Thank you for watching this video, and I hope that you found everything clear and easy to understand.